Welcome back to another video here from the Off-Grid Garage in sunny hot. Well, today with another battery video here. I am going to fully charge the battery again. How exciting is that, huh? How exciting is that to watch an old man in Australia fully charging the battery? Okay, so we are currently at 96%. At least that's what the smart shunt claims. Charging with 41 amps. And this is exactly the reason I want to fully charge the battery. I mean, fully charge the battery. 3.6 as full as possible. These percentage of the smart shunt, they always reset when we balance, when we absorb. You know, this is when we stop charging, and then the smart shunt, accordingly to its settings, it's reset to 100%, and then it gives you the count from there if you discharge the battery. Which is kind of fine, because this is actually the percentage what you are using of your battery. And then at some stage it will also tell you you have 0% state of charge when the battery is at probably 3 volts or something. And this is the amount of energy you can use, the capacity between 100% and 0%. But this is not the true 100% or 0%. And people are always chasing these 10 or 90% state of charge, because you should not really fully charge your battery too often. This causes just more degradation than it needs to be. But where is this 10%? As we know from all these previous tests we have done here and all this what we have learned so far, we cannot use the voltage to determine where is 10%, where is 90% of the battery. So the only measurement we have is the capacity, the ampere hours going out of the battery. And this is something the smart shunt does, and also your BMS does. It counts the ampere hours. As soon as you fully charge, it resets its reading to 100%, and then from there it counts the ampere hours going out of your battery and going in when you charge from solar or from the grid. And then it calculates the state of charge of it. And this is actually the most accurate calculation you can do to determine the state of charge of a battery. The voltage is an indicator, but it's not precise. Well, of course, even counting the ampere hours is not 100% accurate. And that's why the smart shunt or your BMS needs to recalibrate from time to time when you fully charge your battery again. So anyway, this was just the intro. So what I would like to do is now, I would like to charge the battery to 3.65 volts per cell today, and then reset the smart shunt. So this is really 100%. We've got 280 ampere hours of capacity then at 58 volts or whatever it is then. 58.4 it is. So to reach this high voltage, I have to change the settings in my solar charge controllers, of course, which I have done already this morning. I'm charging now to 3.5 volts. I'm just telling you the cell voltages. I don't want to multiply this by 16 all the time, or by 8 or by 2 or by 4, whatever kind of battery you have. So we're just talking about cell voltages. So we start with 3.5 and see how the balance is with the BMS, how much deviation we have then, because it's been a while now since I fully charged again. And well, we had some higher discharge currents here as well, charging the car, and the chainsaw was running in the backyard, and higher currents causing more deviation across your cells. So there might be some balancing happening. But then from there, I want to increase the voltage slowly over time and see if I can reach the 3.6 higher, 3.64, 3.63 volts, as high as possible before the BMS turns off. And then when we reach this voltage, this amazing 3.65 volts, all the cells are equal, all the cells are balanced 100%, we reset the smart shunt. And then I will change the settings in my solar charge controllers back to where they were before. So obviously the battery will then discharge. Yeah, it counts down the ampere hours. And I want to see how much ampere hours are actually missing from the usual absorption voltage I charge to until it would be really 100% full. And that's why I need to do this once to get this calibrated to 100%. And I don't think it is even 10%. 10% would mean 28 ampere hours, right? 280, so 100%, and 10% of that, 28. Absolutely right. And then the next couple of days when I fully charge the battery, so fully charged to 3.45, this will then be not 100% in the smart shunt anymore. It will be more like, I don't know, 93, 94, 95, something like this, I assume. I know we have these tests done before with a single cell, you know, with a battery tester. The birds. I charged the battery to 3.65 and then we charged it only to 3.55, 3.5, 3.4 and determined how much capacity we actually get out of the cell. But I just want to extend this test now to the full battery and really want to see how much is 90% and how much is 10%. But let's start with the full test today with the full calibration, 3.65 volts, 100% state of charge. And then we set everything to 100% and go from there and then let it count down. This will be interesting because now it claims we are at 98%. But I think we are probably at something else. Okay, and here we go. So at the moment we are still charging, yeah, that's our battery voltage, 55.6 volts, 23 amps from one charge controller, still in bulk. And I think I have set the battery to 56, which would be 3.5. So 56, we are almost there, and then we go in absorption. And I have set the absorption time to 10 hours. I just want to keep the voltage at 3.5 and then see what the actual deviation does, and then I increase it slowly. So the BMS had actually time to balance then. It may take the whole afternoon now, but you know, that's just what it is. Okay, let's have a look at the BMS as well. And see how far. Ooh, 70 millivolts we have. Deviation. That is a lot. 3.52. 3.5, 3.5. Well, usually I charge only to. Usually I charge only to 55.2 volts, and we have reached already 56 now. So I usually don't charge that high, and you can see the pack is drifting again, even with no balancing, nothing at all. This is just a normal drift you have in your battery pack if you charge and discharge it over time. And if you charge to these higher voltages, you need to balance. At some stage you need to balance. It gets out of control at some stage. We're almost 100 millivolt off now. I think we have just reached absorption voltage, 56.1. And of course, to make this all work, now we need to change the balance settings here a few times in the BMS as well. Ideally, at this voltage now, 56, we have 3.5 volts per cell now, if they would be all balanced. So I'm setting the balance kick in, turn on voltage at 3.55. Okay, I would say let the battery absorb for a moment here for maybe 20 minutes or so, and then we have another look at the balancing. We are at 105 millivolt at the moment. It may increase a little bit because we are still charging with 30 amps, and then we give it time to balance, and then we increase the voltage from 3.5 to 3.55 and see how far we can push it until. I really don't want to go too high at the beginning because we can see cell number 1 here, 3.555. It's the highest voltage we have, and this is the only one which gets balanced at the moment. And if you go to 3.6 volt now per cell straight away, this one will peak over 3.65 and the BMS will turn off. So we have to be careful, we have to be slow, we have to be mindful what is going to happen. 56.8. Okay, I think I'm confident I'm going up to 56.8 volt absorption voltage in the West Roof solar charge controller. I don't need to change the other one because they are both linked together with this Bluetooth network here, so the other one gets the settings anyway. Okay, so we're increasing the voltage now to 56.8. And there we go, we're already there. And now you can see they're all balancing because we need to change the settings here as well. So this is 3.55. So this would be our absorption voltage per cell, and we need to go a little bit higher. So we probably go to 3.58. So everything above 3.58 will be balanced now. See, 3.6 we have. Still charging with 10 amps. So they all should be at 3.55 at some stage. This one is not even at 3.5. Whoa, number 5 needs to catch up here. Okay, and now after a couple of minutes we can see cell number 5 has now catched up to a 3.51 at least. And deviation is going down to 60 millivolts only from over 120 we had just now. So I'm confident now we can increase the voltage again of the whole pack. 3.55 we had, we go to a 3.57 per cell times 16 would be 57.12. 57.12 in the solar charge controller, green tick. So this is now valid. And now we should see an increase to, well, just a few millivolts in here. But this increases the current again, charges the battery. You can see in cell number 5 how quickly it charges up now. You probably can leave this sitting on 3.6 or something, but I rather increase it a couple of times and see what happens. Then the BMS actually triggers at some stage, and okay, we go to 3.6 now. Confirm. So there we go. 57.2 we have, 3 amps, and everything over 3.6 will be balanced now, which is, oh yeah, we've got quite a few cells, very close. But cell number 5 still needs to catch up. It is still low, but only 64 millivolt now, so it's pretty good. So the drift is actually not as bad as I was explaining it earlier. They're all coming together because if you remember a few videos back, I charged the battery to 3.65 volts per cell and manually balanced it with the lights and the power supply. So I had all the cells very close to 3.65 volts. And then I should have calibrated my smart shunt, right? That is the exactly state I want the battery in again, to calibrate it to 100%. Anyway, we just do it again. It doesn't take that long, actually. I thought I'll spend the whole afternoon in here and increase the voltage step by step, but it's not as bad. 58. Okay, let's go higher. Shall we go 3.6? 3.6 times 16. 57.6. This one is already at 3.6. 57.6. Okay, green tick. And we go quickly back. Increasing the voltage, amps are going up again, and 3.611. Just need to watch cell number 1. Oh. Now the current is tapering off. Good, we have reached the voltage. And we set this one to 3.62. Balance turn on voltage. And let's see what it does. Okay, we've got the 3.666, 3.57 still. Okay, it'll catch up. It'll catch up. We're still charging with 3 amps. As long as my number 1 isn't increasing in voltage. But it looks alright. Okay, give it a few minutes. And then we have another look. And I wanted to really have this calibrated now to 3.65 volt per cell and then reset the smart shunt to 100%. That's the goal. Okay, we are still at 57.6 volts, which is 3.6 per cell. And we have now number 16 and number 1 on the same voltage. 33 millivolt deviation only, totally fine. It's only 2 amps, yeah, we can see here. Number 5 still needs to catch up a little bit, but voltage is increasing here, which is good. And this one gets balanced. And this is the only one. Just changing the balance settings again to 3.61, a little bit lower, 3.62 they were before. See, and now we can see the balancing starting, because if the voltage in these cells is decreasing, the overall voltage is decreasing of the pack, more current is flowing, and we are charging number 5 a little bit faster. This is all a game of balance of single individual cell voltages in combination with the overall voltage then, and then you can set the parameters for your balance turn on voltage very precisely, and you can make it really work with the integrated balancer. We've got 26 millivolt now, and you can see it's increasing now. So we are now at 20 millivolt deviation at 3.6 volts, and we can increase another 0.1 volts, I would say, 57.76, which is then 3.61. Should be, nah, just test it. Green. I don't want to go too high too quickly. And here we've got current again through the battery, and now we watch this cell here, 3.625. Now they're all balancing. We have to increase the balance turn on voltage again to give it more room. This is all a game now with the charge controllers and the BMS and watching and monitoring and then slowly increasing the overall voltage of the pack. I like it. I like this shit. We're getting very close now. I just increased the voltage to 3.62 in the charge controller. And this one was getting very close to 3.64. Yeah, the higher you charge now with the voltages here on your cells, the quicker the battery will react, because we are now in the very, very steep area of the curve. You know, this is the top end of the curve. It's almost going straight up now. And every single change now makes a big difference in voltage. 25 millivolt. It's good. I like it. Okay, give it some time. Okay, next step would be 3.63 volts. Alright, we are now at 3 millivolt deviation at 3.64 something volt. So 2 millivolt. This is like a good red wine. It gets better over time. Now, I mean, this is totally fine now. 2 millivolt deviation at 3.64 volts. So fully balanced the pack again. And now I can reset the smart shunt to 100% state of charge. This is now 100%. And now I change all the settings back in the charge controllers to my standard settings. And then we use the battery as usually and see how much it shows us the state of charge now then with my regular settings. I'm really keen to see how much ampere hours are missing. I think we are very close to 95% state of charge or something with these settings already. But we will find out. So 3.45 volts times 16, 55.2. That's what we're going to put in now. 55.2. So this lowers the voltage now. Float voltage is 3.35. And we need to set the absorption time back from 10 hours probably to 0 hours and 15 minutes. That's all right. Green tick, all good. Yeah, both charge controllers will turn off at the moment because the voltage is far higher than we set. And from now on, it will only discharge the battery. We can see 1.5 amps going out of the battery. And then we will check again how many ampere hours we have actually used from 100% state of charge to our float voltage of 3.35. That'll be the first test to see how much capacity is actually in between. So I guess this will take now 15-20 minutes and then we should hit the float voltage. So after 20 minutes we have now reached the float charge voltage of 53.6 volts, 3.35. Yeah, definitely battery is resting at 3.35 and we are still on 100%. We have discharged 1.5 ampere hours only. 1.5 from 100%. Remember, just a few seconds ago for you, we were on 100% state of charge on 3.6459789. And now we have discharged 1.5 ampere hours only until the float voltage. So that means we are on 99.5% state of charge. There is 1.5 ampere hours discharged float voltage. 0.5%. And this is exactly what I'm expecting. Charging to 3.45 or 3.5 or 3.55 volts will almost 100% charge your battery. There's not much room. There's 1.5 ampere hours only out of 280. So again, there is no reason to charge to a higher voltage. There's no capacity gain at all. Nothing. The only reason to charge to a higher voltage is the battery charges faster. You're getting there faster. You're saving time while charging. But from a capacity perspective, no reason for that. No fucking reason. Okay guys, so far this experiment for today. I will leave the battery as it is, and I will leave the smart shunt as it is. So if you have a look at the VRM, the link is down below in the description. You can actually see all these numbers and figures here on my system live. And we will see in the coming days how this goes. When we charge to 3.45 volts again, absorb a little bit and then go down to float. Charging to 3.45 volts and absorbing is almost 100% state of charge. Well, we will see this again once we discharge the battery now to probably 60-70% today, tonight, and then recharge again tomorrow and see how much percentage it actually has then. That'll be an interesting test for the next couple of days. And we are far, far, far away from a 90% state of charge, what people always trying to achieve. You need to stop charging far earlier and stop absorbing as well. I think it is very, very hard to find this 90% state of charge point. It is definitely not voltage related. Okay, we will see how this goes. As always, guys, thank you so much for watching. Thanks for all your support, all your donations here. And until the next video, stay charged, stay safe, and thanks for watching again. See you then. Bye-bye. Hey, where are you going? You cannot just leave here. You know, the good shit always comes at the end. Here, now after several hours, we are at 90%. So we are now at 90% real state of charge of the battery. 90%. This is what people are aiming for. 90%. And I'll show you here in the VRM. East roof now. No, here. 28.6 ampere hours taken out of the battery. So this is real 90% now. 89.8, okay. So we are now at 90% at 52.8 volts. How do you get there? How do you charge to 90% only and then stop? That is almost impossible. What voltage do you set? What absorption do you set to charge to 90% state of charge? So you have real 10% capacity left until you hit real 100%. Tell me.